Hi, my name is Jacob St.Martin, and I'm the team leader and mechanical design lead of the University of Virginia's NASA Big Idea Challenge team. I'm a fourth-year student studying mechanical engineering, and I'm here today to tell you about BELLE. BELLE stands for the beaming of energy via lasers for lunar exploration, and is a system for remotely delivering energy to rovers or equipment exploring permanently shadowed regions of the moon.
My name is George Wilkes. I'm a PhD in electrical engineering, and I was the lead on the photovoltaic cell and the laser system.
Hello, my name is Rex Serpi. I'm a third-year student studying computer engineering, and I am the embedded systems engineering lead for the team.
Hi, my name is Julia Rudy, and I'm a third-year computer engineering student, and I was working on the gimbal tracking code.
Hello, my name is Edward Lee. I'm a second year at the University of Virginia. I'm an electrical engineering major, and I was the data representation lead.
Hi, my name is David Chen. I am a second year at the University of Virginia studying electrical and computer engineering, and I'm the thermal and radiation lead for the UVA BELLE team.
Exploration of the permanently shadowed regions of the moon poses many challenges. Among the greatest of these challenges is energy. Traditional solar-powered rovers cannot operate in PSRs, and nuclear power is expensive and poses significant safety issues. BELLE is an inexpensive and innovative solution to this problem. The exploration of PSRs is a complex problem and demands a highly interdisciplinary approach to innovation. BELLE was developed through the integration of complex electrical, computer, mechanical, and optical systems. An array of solar panels collects light along the rim of a crater and is used to power a high-powered infrared laser, directed by a control system. This laser is fired to a rover or piece of equipment in the PSR, where a photovoltaic cell converts the light back into electrical energy for use by the rover. A small portion of the light is reflected back and used for tracking. BELLE's innovative optical tracking system eliminates the need for multiple radio communication towers. This is the BELLE laser system. It uses an IPG DLM100 975. Emitting a maximum of 100 watts of laser power at a wavelength of 975 nanometers. The laser light exits through a fiber and passes through this fiber to the collimator head. This collimator emits the beam with a diameter of 8 millimeters and passes to the beam expander, where it is expanded to 24 millimeters. From the beam expander, the beam travels to the galvanometer. The beam is reflected using a system of two motor-controlled mirrors that generate the X and Y motion of the beam. The galvo has a step size of 12 microradians and a repeatability of 8 microradians. The beam then exits and moves on to the photovoltaic cell and retroreflector. The photovoltaic cell converts the beam into electrical energy and transfers this to the board attached to the rover, while the retroreflector returns a small portion of the beam back to the galvo, through the beam expander and to the laser, where there are 4 photodiodes located around the laser. Shown here is the full BELLE system. Extensive 3D modeling, programming, electrical design, and laser and optics design was done to achieve a fully functional and integrated system for power beaming and optical tracking.
Shown here is an overview of our system. The laser beam passes from the fiber collimator to the beam expander, where the beam is widened to reduce divergence. Then the beam enters the galvanometer, where it is directed by a system of 2 motorized mirrors. A searching algorithm is used to locate and lock onto retroreflectors near the solar array, which is mounted on the gimbal on the rover. The gimbal orients the photovoltaic array toward the beam to maximize power generation. The retroreflectors on the gimbal and array return a portion of the beam to the laser, where there are photodiodes that receive the light signal to allow for laser tracking.
As the system is searching for a reflective target, increasingly large concentric circles are drawn until a reflective surface has been hit. Once the beam hits the golf ball, the controllers instruct the galvo to target the location of the reflection and begin tracking. It should be noted that the beam size is optimized for the photovoltaic array, which results in the additional portion of the beam on the wall. As you can see, BELLE is capable of tracking at impressive speeds, and if the reflector can no longer be seen, the searching algorithm resumes. Here you can see the tracking algorithm in action. Before the rover enters the region, the circular search beam can be seen coming from the galvo. As the rover enters the search area, the laser is able to lock onto the retroreflective targets located on the gimbal. Despite the rover changing orientation, the laser is able to easily track the gimbal and solar cell, and if it ever loses the target, it's able to quickly locate it again. As the rover comes to rest, the beam remains locked in place on the solar cell, and it's ready to begin the charging process. And when the rover decides to move again, the sensors detect that change and begin tracking once again.
The gimbal is designed to rotate 360 degrees, so that even if the car is facing away from the laser, the mount will be able to spin until the cell and beam are aligned. To ensure that the cell will be completely illuminated by the beam, there's also a microcontroller that continuously reads the voltage and current signals coming from the cell. Once the microcontroller senses the beam is on the cell, it'll stop the gimbal from spinning and incrementally adjust the yaw and pitch angles until it finds the orientation where the cell is completely illuminated.
Here you can see the beam focused on the solar array. The output of the array is connected to the charging board, whose output is connected to an electronic load, which allows us to simulate the power consumption of a battery. Currently, the solar cell is outputting 2.8 volts at a current of about an amp. The charging board converts this into a usable battery charging characteristic of about 6.6 volts at 276 milliamps.
On behalf of the team and the University of Virginia, I would like to sincerely thank NASA for giving us the opportunity to develop BELLE. Not only have we achieved our goals of power beaming, optical tracking, and power conversion for battery charging, but we have done so in the midst of incredibly difficult circumstances. We have faced many challenges throughout the process, namely those related to the COVID-19 pandemic. But we believe that these challenges have made us stronger as a team. Given the success of this demonstration, we believe that with more development, BELLE could be the key to driving exploration in the upcoming Artemis missions and beyond.